Hello. Good afternoon, everybody. Before we start with the class, I got a request if we have a small question for the homework assignment. So Toma, you asked me a question, so maybe you can give your question either via the chat, if it's a small question, or if it takes too long, we have to do it after the class. But a small question we could handle now. So Toma, do you have a small question or do you have a bigger question you want to ask to me?
Yes, hello. There is a small question maybe we can handle now. That one would be regarding so when we are asked for our thermal flow model to calculate the effective area of the turbine inlet, we just took that to mean that the area that the flow is choked at the turbine inlet and calculated it that way. Would that be the correct way to do it?
That's the correct way to do it, yeah.
Okay, and the second question here is when we start running the turbine at part load, we are asked to compare these effective areas to the one from task. Wait, let me find it. Yeah, so we check the effective area of the turbine inlet at part load conditions, and then we're asked to compare it to the area calculated in the simple model in task 1. Yeah. Is this, how are we comparing part load conditions? What is the let's say, so once we calculated part load, we will get a different area to the full load.
It should be more or less the same. So then this question, why would we have a different area? And please explain. So please explain what you observe. So that's maybe also, yeah, I really want you to explain that there's no wrong or correct. Yeah, there's a correct answer, but I really want you to show that you understand what you're doing. So that's the most important thing here.
Okay, okay. Yeah. Because we do get some differences in our reduced mass flow because the essentially the properties of the gas change and there are differences. So I was just basically wondering when you're sizing these the inlet, which sort of part of this reduced mass flow do you look at, or does this sort of physically take care of itself?
It should physically take care of itself, but we probably have made some simplification in the first task. So you should check that. I think so. It can be partly explained by simplification, but maybe there are also other explanations. So please try to explain what you observe. So that's the main question here.
Okay. So it's open question in a way. Yeah. Okay. Thank you.
Okay, no problem. Okay, I think it's nearly 3:45. So let's start here. Okay, let's start here. So first of all, I would like to do all the best wishes for the 2001 to 2021 year. So it has been a special year 2020. So 2001 hopefully will be better for a lot of us. But I wish you all the best and good luck with your Turbomachinery classes, career, and all the things you are doing here. So all the best for 2021. We start with a good start, of course, in 2021. So we start with Turbomachinery and the class on gas turbine and controls. So that are we going to do today. Wait a minute. I see another thing I have to cancel. Wait a minute. Okay, yeah, I can continue. So this is scheduled for the common classes we still have. Today we are talking about controls. Next Friday, there's preparation for our exam. So that will both be discussed by René Pechnik and me. And on Monday, January 25th, we have the real exam. So I want to have some practical things to discuss with you. So there are 2 homework assignments are outstanding. So the first one is for me about combustion and performance. We just had a discussion about it. I asked to hand it in by coming Friday, I think. So I don't know the other question, please let me know. Maybe we can discuss after class. So that's the homework assignment on combustion and performance. The other homework assignment is from Dr. Vera Popovic on material and mechanical performance. I saw that some external students, non-TUDL students, they can get the homework assignment by sending an email to her. So I think that's the most direct way. And important to know for that homework assignment from material and mechanical aspects, it's not allowed to work in pairs. So you really have to do it on your own. So that's important for that. I think that it has to be handed in by January 13th. So you have a little bit more than a week for that. Are there questions about the homework assignment? Or not organizational question about homework assignments? No, I don't see anything. Otherwise, I can do it via the chat. Double exam is the next question. That's for the best. So yeah, so when will you have the homework assignments? When I'm going to have the result of the first homework assignment, I will ask René when he has corrected them. I think he would have planned to correct them over the holidays. So I will discuss with René Pesnik when we will get the grades from the first assignments. Yes, I think you will get my grades 2 weeks after 2 weeks after next Friday. And I think the same with Vera's homework assignment. So you'll probably get that, well, 2-3 weeks from now. But for the first 2 assignments, I will check with René what the status is of those assignments. So important to know is that for your final grade, it will be 60% of the exam and 40% of the assignments. But the precondition is that your grade for the exam is at least a 5.5. So you should have passed the exam, and the homework assignments can improve your grade. So that's important to know. The sample exams, so there are both for the non-TUDL students and the TUDL student, there are a number of exams on the Brightspace or the Google Drive, so you can practice with them. With the number of exams, we also included the answers. Not for all exams, but I think it's really for practicing. You can find out the answers themselves. It's good for practicing. For the number of exams, we included the answers. And we will discuss one of these exams coming Friday. So we will discuss, we have discussed with René what exam we're going to discuss coming Friday, but one of the exams we will discuss coming Friday. Then at January 25th, there are some people from maritime engineering. I think 2 people announced them to me that they have a double exam on January 25th at the same time. So for those people, and I can only accommodate at maximum 2 or 3 people, we can arrange something separately. So in that case, 2 or 3 people can have another exam session on a Friday on the TU Delft and proctored by me. So we will plan their separate session for those 2 or 3 people who have a double exam on January 25th. So please make yourself knowledgeable to me as soon as possible, because first come, first serve. I want now registered for the double exam. So the exam at my office, not on January 25th, but if other people's are, please send me an email, and I can only accommodate 2 other people. So it is first come, first serve. Otherwise, you have to go to the resit in April if you can't, if you are too late with announcing now. So those are the practical announcements. Are there some questions about them? Okay. Now, then we go further with the class about controls. So actually what I really want to discuss is the learning objective of today is the control principles of a gas turbine and what's the basic control setup. We will discuss, and I'd also like you to understand the control of the speed and the load. And very important is actually that's the main controller is the inverse actually control of the turbine inlet temperature via the exhaust temperature. And I think that's one of the main control. That's one of the main control parameters of a gas turbine. And beneath that, active secondary control are the combustion controls. And we'll also discuss the start-stop of the engine with a different phase in that. Important actually, and I think that's also important because there are real controls engineers in this meeting. So we will really brief discuss control on a little bit abstract level. And yeah, in reality, you always have a separation between controls and safeguarding of the engine. Actually, in this lecture, they are mixed up. I don't make a real explicit separation between controls and safeguarding because we really view it from a process point of view. But in reality, from a controls perspective, you should make a difference between controls and safeguarding. But okay, that's not be discussed today. So if you are a real hardcore controls engineer, yeah, you may sometimes doubt the terms I use today, but I talk in general about controls, but I also mean safeguarding with that. It's important for the hardcore controls engineers. I see a question from Luca. On what Friday will the other exam take place? Well, I will make a proposal about that. I think we can agree on that. So the double exam for the people from maritime engineering, we can agree on the date for the other exam. There's no issue. We can agree on that. It's one of the Fridays in February, probably. So this is what we're going to learn today. It's really about the basic controls for the gas turbine. So why do we need controls? So maybe via chat, why do we need controls for a gas turbine, for both controls and for safeguarding of the gas turbines? So what are the reasons why we need controls? For protection and safety, and just anybody, so you can answer via the chat, what should we prevent a gas turbine for? Temperature, power, and speed, yeah. Variation in required output, overheating, surge and stall, yeah, that's good. I see some good answers coming by. Some more questions, then we can discuss them. Okay, let's start with the top one. So protection and safety, temperature, power, and speed. Well, speed, you need to control the speed to prevent overspeed. We come back to that later. So you don't want to have overspeed of the rotor. Power, I think that's not really for protection and safety. That's really more for, well, your commercial reasons. You want to deliver a certain amount of power. And the temperature, you also want to control the temperatures of important part of the unit. That's good. Well, variation in required output, that's the next answer. Well, okay, that's also not as more commercial than really required from safety. Overheating, that's a very important one. I now read it from the comments. That's an important one, so you don't want to get it overheated to prevent damage to this engine. Surge and stall, that's an important one. So you should prevent the compressor for surge and stall. Turbine inlet temperature limit, yes, the same. Overspeed, we just had it, overspeed. Humming, that's also an important one, combustion dynamics. So we come back to that later. So yeah, we call it now humming, but actually there are acoustic vibrations in the combustion chamber that you want to prevent. Combustion dynamics, vibration. Yeah, vibration, you normally can't control. Combustion dynamics you can control by tuning the combustion. Vibration you normally can't control by the controller. You should just have a well-designed and well alignment of the machine. So if you look at protection safety, we come to that. What do we see there? So high temperatures. And I think there are a number of things they cause immediate damage or they cause damage on long term. Some background now, sorry about that. So I think high temperatures, in most cases, they are not an immediate threat. they're more in threat for life consumption. High temperatures, you get more creep, fatigue, and oxidation discussed in the classes from Vera Popovic. And you really want to prevent high temperatures to reduce life consumption to maximize the life of the unit. Surge stall, that's very important. That's immediate effect. I show you a picture in the next slide where you can see the effect of surge and stall. Transient. So important here is that you can thermal gradients, thermal stresses, and you want to control them. You don't want to have them too high, otherwise you get fatigue damage to your engine. A very important one is the maximum rotational speed, and they normally call it overspeed. When a gas turbine engine is running and it's a big amount of mass, there's a lot of energy in running that engine. And then if that is something, if you get overspeed, so there are a lot of high stresses in such a motor, and if you get overspeed, some cracks may occur and some parts may get loose. And with overspeed, you get an immediate, very large release of energy. And that really has to, well, it really gives to a lot of damage. We have the next slide of a picture from that. Loss of flame flashback, that's important. You want stable operation. And of course, high pressures you want to prevent. Well, then we get the control of the power thrust video shown. That's really for the power and thrust is really for the commercial operation. So what are you going to serve with your unit? The speed. So especially if you are, for example, driving a compressor or a pump, you want to control the speed, efficiencies, emissions. Humming should be included here. Active humming and from combustion dynamics, I should include them next time. And I think very important are the transients. So the sequences, startup, shutdown, acceleration, deceleration. So you really need a gas turbine to control. Well, here you see some damages if you don't have good control. So here on the top left corner, you see some damages from an overspeed damage. It is in case from a steam turbine, where you could have similar damages from a gas turbine. And that is really one of the main, most important things you have to look at when you work with rotational, with turbomachinery. Some weeks ago, I talked to a steam turbine controls engineers and said one of the most important things for controls engineer for steam turbine is overspeed, overspeed, and overspeed. Those are the three most important things to control for a steam turbine. For gas turbine, it's a little bit also, but I think overspeed is one of the most important things to control to really to prevent damages like this. The bottom left picture is about surge damage from axial compressor. So really it's from an aerojet, an jet engine, where surge and stall occurred in an axial compressor. And because of the high reverse flow and the high shock waves created by that, you get liberation of blades, and this is the damage of that. So this damage in this axial compressor is caused by imperfect surge control. Well, this is an example on the top right. This one is an example of combustion flashback. So when the flame speed of the flame becomes higher than the local flow velocity, you can have flame attachment to the burner, and you can have, well, burners like this. And in this case, your burners damage, you get all kinds of effects on emissions, efficiency, and things like that. And on the top, the bottom right, you see here, well, I can have a little number of pictures, but this is really damage to first stage buckets. So the first stage blades, first stage vanes, and it really has to do with the high temperatures. So you didn't have enough cooling here on the end of the blade, and therefore, in combination with the materials here, you get damage to the blade. And it can also lead to sequential damage. So really to prevent all these kinds of damages, you need controls. And it's important to know, actually, wait a minute, go here. So what is important now if you get a dual shaft gas turbine. So what do we want to control? We want to control the load, the thrust, N2, so the rotation speed of the power turbine. That also directly linked to N1, as we saw in the class on performance. Compressor stall and surge. That really has to do with the N1. So here's just the compression here. and the highest temperature, that's TO3, the thermal inlet temperature, and first also the fuel-air ratio. So this is really what we normally want to control with such an engine. And important to know is that you only have very limited control parameters you can use to control the engine. There we're going to. You can either have the fuel valve, the IGVs, and the bleed valve. So in principle, for all gas turbines, you only have 3 control parameters, where the main controller is the fuel valve to control the fuel flow. With the IGVs, in that guide range, you control more or less the mass flow, and you can use them during startup to prevent surge and stall. And then the bleed in the compressor, you bleed that you use during startup to prevent surge and stall. There are some other tricks. This for standard gas turbine, you could have some inlet air heating, but I think that is some inlet air heating or compressor air recirculation or some other secondary controls you could use. But these three, the fuel flow, inlet guide vanes, and the bleed valves are the most important, actually the only things you can use to control all those things we saw in the previous slides. So you really have to have a smart control to really control all those parameters with this limited number of control parameters. If you look like a military engine, for example, a jet engine, you can also have an afterburner and thruster reflector. So the afterburner you can use to generate extra thrust, and the thrust reflector, yeah, you can change the angle of thrust. But I think that's for gas turbines for power generation, that's less relevant. But important to know is really there's only those 3 parameters you can use to control the gas turbine. If you remember from some class on performance, we make it all the set of equations that describe a gas turbine and the set of independent variables. And actually, you saw if you leave out the IGV and the bleed, that is also 1 degree of freedom. And the degree of freedom is normally the fuel flow. So what are the inlet guide vanes? So now look an axial compressor. So the air is coming from the left to the right. So you see here the first row of stator vanes, and it's the first row of the rotor vanes. So the rotating vanes, the rotor, stator, rotor, stator, rotor. And actually what you can do is change the angle of the blades to change the angle of these stator vanes. So in this case, there are 4 rows of IGVs. In all the gas turbines, there are only 1 row of IGVs. And actually by controlling these positions, so the angle of these vanes, you get another angle of attack for the first rotor vanes. And thereby actually you can modulate the inlet airflow. So typically, if you have a constant speed air engine, you can typically, and maybe if you have a little better design, 70%, but typically you can vary the airflow between 80% and 100%. The risk if you go below that, say 80% or 70%, you can run into surge and stall, especially stall at surge. Stall at a late stage. You can especially run it stall at a late stage. So therefore, normally this amount of airflow reduction is really limited by the prevention of stall. So the ITVs can either be 1 row or 4 rows in this case. You get some small effect on the compressor efficiency, but the impact on the compressor efficiency is very limited. And you use those ITV for 2 applications, as I told. First of all, is during startup to reduce the mass flow to prevent surge and stall and to prevent stallsations. And the other way is during part load operations to reduce the mass flow. And especially very important when you apply a gas turbine in a combined cycle installation, you really can, by reducing the mass flow on part load, actually you reduce the mass flow that exits the stack, and therefore you can increase the efficiency even a little bit. So parted operation, normally you get a best parted operation by playing with these ITVs. Then we have the bleed valves. So the bleed valves are located somewhere at the end of the compressor, halfway at the end of the compressor, and is really to prevent upstream stages to stall, just to create flow to the gas turbine. And they normally use during startup. And you actually you bleed off expensive compressor air. So you take a lot of energy to pressurize this air. So it is really a pressure loss. So therefore, you only want to use it during a startup. During normal operation, you don't use them. Well, with surge stall, I think we discussed that in detail during the classes on the compressor curves. So I'm not going to discuss it further here, but that's very important during startup, mainly at startup and off design operation. You really have to be very careful with surge and stall. Like I said, well, we go back later. Okay. Then the very basics about control is really a kind of P&ID loop. So you have a kind of parameter you want to control. You have a controller, you have an actuator, and that influences the process, and you get the output. So that's normally how it looks. So the process is, for example, the output is, for example, the power. You measure the power. You see there's a set point of the power. See a deviation. Well, you then have a controller that determines if you have this error. Then it, for example, controls the gas flow. So if in deviation of power versus the set point, you get an error. The controller determines the new setting for the gas valve, and the gas valve opens or closes, and thereby the gas turbine will generate more or less power, and that will be measured. You get the closed loop. So this normal P&ID controller, and a PID controller. Well, you have a number of things. That's why it's called PID. So the P is proportional. The I is integral, so to get long-term stability, so you can average out over time, and the D is derivative, so you can really fastly react on changes with a certain constant before them. So these are the typical standard control systems. I don't go in detail. I think about control theory and other things like that. You can have more of a background in it, but this is normal controls that also are applied in gas turbines. So if you look at what is the controls for the normal operation, and actually, if you look like a single shaft gas turbine, the max power. So actually, if you run, normally called base load, we call it temperature control. So we come back to that later, but actually, then you really have one operation point. You have the ITVs fully open, and then you control the outlet temperature by controlling the fuel flow. You can also have power control. So in that way, actually, you have to both control the power and the highest efficiencies, the high turbine inlet temperature. So then you have to control two parameters. And you can control speed. So if you, for example, are running in an island operation, so not connected to the main grid, but on a small subgrid, and you have to control the frequency of that small grid, or you have to control, in the single shaft, you normally don't have a compressor. So you really have to go to the grid control. You can also have speed control. And during startup, of course, where you're not connected to the main grid, you also have speed control, because then you have to ramp up to 3000 RPM speed, 50 Hertz speed. So these are the normal controls for a single shaft. For a multi-shaft, actually, it's the first two are identical to the single shaft. So the power control and the part load, the max power and base load, so the ITVs are fully open. Then you have the speed control of the power turbine. That's really when you are linked to drive the compressor or pump or something like that. That really has to, when the matching of the power curve from the turbine matches the consumption curve from the driven equipment. So that's important here, like we show here. And there you have, in combination with speed and gas generator control, where we saw in previous classes that actually that's all linked together. So if you have a set point from the power turbine, automatically the gas generator will adopt to supply the right amount of gases for the power turbine. So that's important. This combination of you also control this one with the multi-shaft. So there's a big advantage of the multi-shaft versus the single shaft, that you have the speed control of the power turbine. where in a multi-single cell that's more actually not really possible. Important to know here, and I'd like to discuss a little bit further, because this is the most important parameter for gas turbine controls. And it's really for, like I said, you really want to control the TO3, so the turbine inlet temperature. Does anybody know, would it be possible to measure that TO3, so the turbine inlet temperature, and how would you be able to measure it? I see it now coming by. Oh, infrared sensors, yeah. Yeah, well, in reality, I don't, well, actually, it's quite difficult. I think in theory it might be possible, but you want TO3, you really want to, with infrared sensors, you measure the temperature of the metal, so not of the gas. And like we said before, you have quite some cooling films between the metal and the gas to prevent overheating of the metal. So I think infrared measures will not be possible, because then you only measure the metal temperature. So you should really measure the flue gas temperature. So then you should have maybe a local thermocouple in the flow. That will be very difficult with a high temperature. So for example, well, modern gas turbines are 1600 C, it's very high temperatures. So what normally is done is indirectly calculate the TO3 out of the outer temperature. The outer temperature of the gas turbine is typically 500, 600 centigrade. So you can really measure that with quite a normal thermocouple. And actually, by inferring it from the turbine efficiency calculations, you can calculate this TO3. I try to make a simple calculation. So if you have this one, here, wait a minute. So if you have this turbine with TO3, TO4, PO3, and PO4. So from the thermodynamic, isotopic thermodynamic relationships, we know that TO4 over TO3 is PO4. So it's isentropic, of course, PO4 over PO3, gamma minus 1 over gamma. So that's the isotropic relationship. So you can work it out. TO4 isentropic is times TO3. So this is really, so you can calculate the isentropic T of, sorry, I made a mistake. Yeah, okay, yeah, that's T of, wait a minute, yeah. I can better formulate the other way around. Wait a minute.
Yes.
I make it the other way around. Sorry about that. TO3 times TO4. Isotropic is PO3 over PO4 gamma minus 1 over gamma. So we measured TO4, so we can calculate TO3 isotropic is PO3 over PO4 gamma minus 1 gamma times TO4. So with this relationship, we can calculate the real TO3 real. Then we have to calculate the isotopic efficiency is TO4 minus delta T isotropic times times the turbo efficiency. So you really make that the isentropic delta T of a turbine is larger than the the isotopic turbine delta T is larger than the real isotopic turbine efficiency, the real delta T of a turbine. So we know TO4 minus TO4 minus isotopic. So in this way, we can calculate using the isotopic efficiency, the turbine efficiency. Wait a minute, I'm putting on my headphones because the cleaning is going on here and it's a little bit noise background. Wait a minute. So, I'm back again. Okay. So the question actually shouldn't be TO4 but delta T efficiency. That's just what you take as a starting point. So I now assume TO4 to be known, and I want to calculate TO3. So because that's what you don't know, and either you have to add the delta T to TO3, or you have to subtract it from TO4. It's just the other formulation around. Important here is to know, and that's very important here, is that what for a turbine is that the real temperature difference of the turbine, so the real work generation of the turbine is smaller than the isentropic temperature difference of the turbine. So that's what you see here. So the delta T real is smaller. So this delta T real is smaller than delta T isentropic because we have losses. So if we calculate like this, I mean, you can do a number of calculations for this. But really, if you do it like this, so I can do some calculations here. I showed a picture here, but if you normally plot a figure like this, so if you want to have a TO3 is constant, so that's the assumption. Then you have here the pressure ratio, so that is PO3 over PO4. So that's the pressure ratio. So that's, for example, 5, 10, 15. Well, we had the all the way calculation. Then you calculate, for example, if the TO yeah, wait a minute. I'm sorry about I messed myself a little bit up. Okay, let's go. I go back to the roots again. So we have the same equation. I think we had a good equation. So we have this equation. We go to this equation. Sorry for the mess, but we have this equation: TO4 divided by TO3 isotropic is PO4 divided by PO3 isotropic. So TO4 isentropic is PO4 of PO3 times TO3.
And then we also know that, so you're right about that. So TO4 real, TO4 real is TO3 minus TO4 real is the TO4 delta T isotropic at the turbine. So TO4 real is TO3 minus TO3 minus PO4 divided by PO3, comma TO3. Important here is actually, so here you see PO4 over PO3. And that is actually, if you, so that is PO, so normally this PO4 over PO3, and here's it PO3 over PO4 standing. But if you work that out, so if you have TO3 constant, for example, if you assume there, for example, 1500 Kelvin, and you take PO3 over PO4 is 15, so the pressure rate is at 15. So PO4 over PO3 is 1 over 15. Then you can calculate TO4 isentropic is, in this case, I worked it out in Excel. For example, at 15 is 802 Kelvin, and TO4 real is higher. Is in this case, if you, for example, assume 90% efficiency, you come to 872 Kelvin. So if you look, for example, like this, you come to 872. You can do the same for 10. And that's important. For 10, the outlet temperature will be higher. So you have the same turbine inlet temperature, but the outlet temperature will be higher because you have a smaller pressure ratio over the turbine. So you get the curve something like this, where here is called TO4, and on the x-axis is the pressure ratio. And this is one of the most important curves for the gas turbine controls. Because if you control the gas turbine, the outlet temperature to stay on this curve, you assure that you have a constant turbine inlet temperature, so the highest efficiency. So this is one of the most important curves in gas turbine control to really assure that you operate on this curve. And you can operate on the curve. You can operate on the curve by controlling both the ITVs and both the turbine inlet temperatures. I have a question. So what happens if we close the IGV? So what happens with the pressure ratio? Can somebody answer that question? I think it lower, and why would it lower the pressure ratio? I'll check with the chat again. Chat. I think it lowers, and then the number of goes down. Well, it lowers, but because actually, if you see like here, if you have less air to the compressor, you get here, because you have a choked flow here, you get less mass flow at the choked nozzle at the inlet of the turbine, and therefore the pressure ratio goes down. So if you close the IGVs, you follow this curve. That's important to know. So this is really by closing IGVs, you control with the same turbine inlet temperature, you follow this curve. I have another question, wait a minute. Okay. We had that question, and then from J. Vrijns we have a question. If you use the same J. Freund, there's a difference in results for calculating this work. J. Freund, can you please open your phone so maybe you can more better explain your question? Share the screen. I get a laptop with it. Maybe we park this question later in the class. So there's questions really about the calculation of the turbine inlet temperature, the turbine efficiency. Yeah, so we will park this class for later. Okay, a bird question for later. So important here is really this one of the most important curves in gas turbine control, where you control the exhaust temperature versus the pressure ratio. And important to know is with the constant turbine inlet temperature, you get an increase in the exhaust with a decreasing pressure ratio, you get an increase in the exhaust temperature. And this, for example, the typically design where actually in reality is not a real straight line. So in reality, in the gas turbine control system, they normally make their straight line out of it. So you see here the compressor ratio and the exhaust thermocouples. So the terminology you've seen here has been used for General Electric, but all the manufacturers use similar terminology. But you really see here the compressor ratio, and you see this curve because of the constant firing temperature. And then that hits a kind of isotherm, it's normally called. And this is normally the maximum allowable temperature at the exit of the gas turbine. So at the exit of the gas turbine, because of the ducting of the material choice at the outlet of the gas turbine, you have a limit there, and it's limited by the thermal line. So you normally follow this line up to here, and then you go further like this situation. And on this line, you both control the IGVs and the fuel flow to stay on this line. So that's really the trick. You really try to do it. So this line is normally part load line or the power control line. If you really want to control the power of your gas turbine, you work on this line where you control both the IGV settings and the fuel flow. You really want to have two conditions. So you want to be on this line and you want to match the power. This temperature at the exhaust thermocouple is measured by a lot of thermocouples. So you take the average or the mean from them, depends a little bit on the situation, but you may take the best situation for that. Then there's a definition that is base load. A base load is normally when you are at the end of this line, ICVs are fully open. So when you are at the end of this line, you can have that you have a different line, and then that line, that control line, you only control the fuel flow because the IGVs are fully open. Does anybody have an idea how this line would look like? It's not flat. No, it's not a flat line. We go back to it later. If you these are the thermocouples, so I'll come back to later. I have a click for the plate later. So these are the number of thermocouples. For example, this gas turbine with 14 combustion chambers, you have 27 thermocouples to measure the temperature. And this is how the controller normally looks like. Wait a minute. So actually, if you really look like, so what do you want to control? You want to control the speed or the power. So in most cases, you want to control the power and the exhaust temperature. So these are the measured parameters, and it go into the controller. So you normally have a speed controller that's called the governor. And therefore the power can also be converted to a kind of speed value. And you have the temperature control, exhaust temperature controller. So the exhaust temperature controller both controls the IGVs, and if those cannot be closed anymore, it also controls the fuel. And with the power controller, it takes the combination of those two parameters to control the fuel, and that goes to the gas turbine. So you have both fuel and the IGVs are controlled with these two set points, the speed and the exhaust temperature. And that's really what we saw here. So if you look like this curve, the IGVs normally close at 80% load. So normally if you go to this curve back again, here, normally at something like here, you're 80% load and the ITVs are fully closed. So you follow this curve, you normally about 80% load, your ITVs are there closed. Does anybody have an idea? So for the part load control, how can we also control the part load? Does anybody else have an idea how, besides the ITVs and the fuel flow, we could also control part load? What would be another parameter to control part load? Yeah, I think, well, I see the answer in the question in the comment is the air preheater. Yes. If you really want to control the load, like we saw, you can either do it with the ITVs, so to decrease the mass flow of air, but you can also decrease the mass flow of air by increasing the temperature of the air. So if you really look like a compressor, you have the corrected mass flow. And actually by increasing the inner temperature of the air, in fact, you suck in less mass flow of air. And by sucking in less mass flow of air, there's going less mass flow to the system, and thereby you will have a lower mass flow to the system and thereby a lower load generation. And there are two possibilities. So you can have the inlet air, you can have external heat, but you can also have compressor air recirculation. So you tap off at the end of the compressor and you let it in at the inlet of the compressor. Of course, there's also an additional effect because actually in this case, you are actually destroying power because the compressors use a lot of power to compress the air. And that is one-to-one by this air circulation, you get rid of that pressurized air and convert it into heat only. So this is really here, that's the additional effect. You get also more power reduction by this. It's not good for the efficiency, but for other reasons, it's often used compressor air recirculation part of the operation. One of the things is there, because you use this to get deeper part load. So to get actually the ITVs, you can only go to 70, 80%, but with compressor air recirculation in combination with ITVs, you can go to 50, 60% part load operation. And the other things is by compressor air recirculation, you actually increase the inner temperature of the air. And that also leads to an increase in outlet temperature of the air. And that also has some advantage for stable combustion. So in their way, you can also, because you have higher temperature, you could also have a longer range of stable dry down NOx combustion. So besides part of operations, also for very often used for combustion stability. Well, this is typically control curve, and actually this is really where we were under this one. So in this case, where we call it T-fire max, so you have the gas turbine load. Actually, it should be the compressor ratio on so it should be the compressor ratio on the x-axis and the exhaust temperature. So if you really go from full load, then you close the IGVs and you want a certain gas turbine load, you follow this curve. So you control for the outlet temperature with the controller IDSOL. At a certain moment, you hit the maximum allowable outlet temperature. In that case, you follow the isotherm here. And at certain locations, your ITVs are fully closed. So normally they can modulate between 50 and 90% or about 50% open. So if the ITVs, the inlet guide vanes are fully closed, so they're only 50% open, then the only thing you control, because you cannot control the ITVs anymore, in this case, you control only the fuel flow. And you go to this one. So this is really the only fuel flow situation with the constant ITVs. If you look at the baseload situation, where you have the ITVs fully open, actually, you also see here in this case, that you more or less have the same curve. So actually all those curves for same ITVs, these more or less all lines in this paragraph. So if you would, for example, go from this point down with the same ITV, you would go have a curve like this. And if you go at maximum load, so the max ITV fully open, you will also have a curve like this. Does anybody know? Well, at this situation, so we can't control the mass flow of air with the ITVs. Why are there still variation on this curve? What would be the reason for variation on this curve? Yeah, I see the answer already coming by. That is really, oh, sorry, it's really ambient conditions. So for example, with a low ambient temperature or a high ambient pressure, in that case, you have air with a high density. So you suck in more air at the same flow. And in that case, you will have a higher pressure ratio. So then you will be on this side. And with the lower temperatures, or with high temperatures, so the higher inlet temperature, so lower density of the inlet air, you will be more or less on the other side of the curve. So this is really, if you control it with the maximum ITV and control it on this curve. So this is really when you go from base load, full load back to zero, you go like this. And if you go from min load to full load, you normally follow this curve. Here's min ITVs. Then then you hit the isotherm. When you hit the isotherm, so the maximum allowable outer temperature, you gradually increase the ITVs opening, and then you follow this curve to have the constant fire temperature. So these are the most important curves, and this is really a very important curve for gas turbine operation. So this is a typical control curve. Does anybody have questions about this curve? Yes, a similar curve, more or less a similar curve to the first question. Does this apply also to aero engine? Yes, this question can also, this curve more or less also applies to aero engines. You have a little bit difference, but actually, then you actually treat more or less the power turbine and the gas generator turbine as one, but you have more or less the same control curve for an aero engine, not for an, for an aeroderivative engine. For an aero engine, actually, if you look like an engine that's under an airplane, they only control for the thrust. So actually, they don't look at the isotherm. They don't look at the maximum allowable inlet temperature. It's just maximum thrust. So that's a little bit more simple control there. So then is the question, can you repeat how the isotherm is maintained? Yeah, I go two slides back. So actually what happens here, if you keep this picture in head, if you go 2 slides back, actually you should go like this. So this is how it more or less worked. So for example, you set a speed set point. You get the speed set point, for example, 100% load that puts in here. And that really, there you have here, so the speed controller or the power controller, and it gives a set point for the load, if there should be more or less fuel added to this point. On the other side, there's also an input here from an exhaust temperature set point. So you have the exhaust temperature set point that comes from that control curve we just saw. So that's the input from here. Depending on the measured compressor ratio. So depending on the measured compressor ratio here, like here. So here on the dependent compressor ratio, it calculates what should be the exhaust temperature set point. That exhaust temperature set point goes into this controller. And this controller, it's a little bit, it's quite a complex controller that both gives a new set point for the IGVs and for the fuel. And this joint controller controls the gas turbine, and that way it's controlled to keep it on this maximum temperature line. And for the isotherm, it's exactly the same. Then it just reads the CPD, so the compressor ratio. It sees what's an allowable exhaust temperature, and this combination of these two controllers really tries to keep both, to achieve both the power and to keep this exhaust temperature on the exhaust temperature from the sphere. Even kijken. Er is een other question. Why should we run max? Yeah, actually run max on IGV max. Actually, if you left this question, why should we run max temperature on IGV max? Actually, there also you have the max in the temperature control at that situation. So you also have there the max in the temperature controller. Then it's a question on max IGV. We also like to have the max power output. Is that we also go to the max outer thermocouple? Yes. On max, we also like to have the max output. Yeah, but if you really want to go to the max outlet thermocouple, I think that's OTC. I think that's a Siemens terminology, but I think that's a maximum outlet temperature couple. But you should prevent that your turbine inlet temperature comes too high. So that's why you still need a kind of control for that to control the inlet turbine inlet temperature. So therefore, yes, actually in aero engines, they do it. They just go to the max outlet temperature to really get the max power out of it. But for power-based engines, where you are running a longer time on this max power, you really want to control the turbine inlet temperature. And therefore, you just can't go to the maximum outlet temperature. Because the maximum outlet temperature would be the isotherm. In either case, you really would like, if you really like what you say, if the max outlet temperature is the isotherm, if you would continue that to the right side, the higher pressure ratios, actually you would have a significant increase in the firing temperature. So in the turbine inlet temperature. Firing temperature is another, this is really a general electric terminology for turbine inlet temperature. Okay, let's have a short break and then we continue in 5 minutes from this. Then we go about combustion controls.
All right. So my question was about, we were talking earlier in this lecture about the turbine, basically the turbine work. And if you have a turbine efficiency, and you would use that to calculate the work, wouldn't there be a difference if you use the turbine efficiency to calculate the real temperatures and then calculate the work instead of calculating the isentropic temperatures and then calculate the work using the efficiency?
It should end up with the same, I think, but we can try to do the same. So let's try to explain it. So what is the situation? T3, T4, it'll P3, T4. So we can calculate, well, like for example, we know P3 is, for example, 15, P4 is 1, T4 T3 is 1500 K, for example. Let's assume that. Okay, then we can calculate the isentropic. T4 isentropic is P4 divided by P3, comma, comma, T3. You agree with this? So this is really how you can calculate this. So in this case situation, this T4 isentropic. Then you can calculate, of course, the delta T isentropic is T3 minus T4 isentropic. Delta T real is delta T isentropic times turbine efficiency. Well, we know this one, and that is T4 minus T3. So the delta H real is the entropy difference is Cp times delta T real. We assume now very simple that with constant Cp, make life a little bit simple. So we can as Cp T4 minus T3, and the work is the mass flow times delta H real is mass flow Cp T4 minus T3. You agree with this, or? Yes, okay. And
I think I made a mistake in that I was thinking about the polytropic efficiency, I think, in which the efficiency is in the exponent, so then it changes.
Yeah, the polytropic efficiency, but we will now work with the isotropic efficiency. Polytropic efficiency gets a little bit different. Yeah, that's true. Yeah, yeah. But this with the isotropic efficiency. Now with the polytropic efficiency, well, it's actually still the same, because then you also calculate the isotropic, but then it is there in the polytropic situation. Then you get something T for real is T4 T3 at the polytropic gamma minus 1 over gamma T3. And then, yeah, okay, the polytropic is sometimes a little bit easy because you don't have that simple correction, but then you can calculate from here, you can have the same calculation as we just showed there. Okay. I have a question from Matteo Bernoulli. In the control curve, when we are at the isothermal line, are still close to ITVs? Yes, they are still close to ITVs. So at the end of the isotherm, you're at min ITVs, and then you can't close the ITVs anymore. So then the only thing you can do is really reduce the gas flow, the fuel flow, and therefore you go down in the exhaust temperature also. So now I take a break for 2 minutes and then I come back. Okay, let's start again. Some problems with unmuting. So if you really look at the combustion controls, the main control you discuss part load, exhaust temperature, exit temperature, exhaust temperature control. So that's the main control we just discussed. And then we have the combustion control. And my question actually is, can we control, if you have the main control, so that's the really important control, and we can control the combustion control, maybe the secondary control, can we freely control the fuel-air ratio? Or can't we? So the question is it possible with this main control, when we have this main control, that we above that, we can also freely control the fuel-air ratio? No, I think that's very important. We cannot. Now that's very important because actually the mass flow is really given by the settings of the IGVs. The fuel flow is really given by the settings of the gas valve. So really, because those controls both the power and the we want of the exit temperature, then we cannot control the fuel-air ratio. And does anybody has an idea what's if we are at if we are at the control curve we show here? For this control curve, so with a constant turbine inlet temperature, what happens on this curve with the fuel-air ratio? What does the fuel-air ratio change over this curve, or what happens with the fuel-air ratio in the combustor over the whole? Yeah, you're fully about it. I see stays constant. Yeah, that's very important to realize that actually in this range where you have a constant turbine inlet temperature, you also have nearly a constant fuel-air ratio, because the fuel-air ratio is actually, like we discussed during the combustion class, is the adiabatic flame temperature is a function of the fuel-air ratio. So we can go to the curves again. So if you have that, if you have the so if you remember good from the have a curve like this. So if V is 1 and that's T stoichiometries, so it's stoichiometric, that's the maximum flame temperature. And in this situation, you have a lower flame temperature, but you have excess of air you have to heat up with that fuel. And with the combustion and within the gas turbine, normal something like V is 0.4, 0.5, something like that. Depends a little where you are in the combustor. So really that determines the fuel-air ratio. So it really, because you have a constant turbine inlet temperature, that means you will also have more or less a constant adiabatic flame temperature. And if you have the average at this equivalent ratio, that will keep the fuel-air ratio stay more or less constant. You have a small variation, and the variation is mainly caused by the changing exit temperature of the compressor. Because if you look like this, if you make an energy balance over the combustor, you have here the mass flow of air from the compressor and the temperature of air. You have here the mass flow of fuel, and you have a turbine and a turbine inlet temperature. And you see, if you make a heat balance over the system, if you will have a higher inlet temperature, you will also have, if you have the same mass flow fuel, we also have the same turbine inlet temperature, the higher turbine inlet temperature. So in reality, because you want turbine inlet temperature to be constant, that will change the fuel-air ratio. So you have a little bit curve like this for different turbine inlet temperatures. And then you will change here with the fuel-air ratio at the same turbine inlet temperature, depending on the compressor, different air temperatures, depending on the compressor air temperature. So this is important. In this situation, you have the same fuel-air ratio at the same turbine inlet temperature. But the trick is actually, and that's actually what happens, you can distribute the fuel over different injectors. And that's normally when you go from part load to fuel, for part load to full load, you really have to distribute it to guarantee stable combustion. So if you look at combustion controls, what do we want to have? So the most important one is a stable flame. And the second one is emissions. And the third one, I should include it here, is also dynamics, combustion dynamics. So if we really look at the discussed during the combustion class, we see two key types of combustion. So you have the premix combustions. So that is dry or NOx. So where you premix the fuel and the air before you enter the combustor. And therefore, we know that there's only a stable flame only in a small fuel-air ratio range. Either you get very high NOx emissions. If you have a high fuel-air ratio, so you have too much fuel, you get high temperatures and therefore a stable flame but high emissions. And if you want to have low emissions, you have a low flame temperature, but if the flame temperature comes too low, you get an unstable flame. And we can control the fuel-air ratio by keeping the IGV control. So keeping on that line, really that constant turbine inlet temperature control line. So really see then you have non-premix combustion. So they are actually the fuel and the air enter separately in the combustor. They mix in the combustor and the combustion takes place at the interface between fuel and air. And in that case, what you can do there, because at the interface between fuel and air, you always have the stoichiometric flame temperature and therefore stable combustion, high temperature, stable combustion with high emissions, unfortunately, but you can have stable situation there. What you can do here, for example, at part load, so really premix combustion, you can only operate with this IGV control to keep it in that range, to keep it in the fuel air ratio range. Non-premix combustion can do it over larger range. And if the range becomes too large, you can switch off fuel injectors. So at low loads, you can maybe run on one fuel injector, and at the high loads, you can run on more fuel injectors. So that are the tricks you can do to do it. So if you really look like it, equivalent rate, stable combustion, so lean and rich attention where we are here. We should do it in between it. And this is a situation here. So that's why you really want to control the fuel air ratio for premix combustion. So this is the typically combustion temperature. So the adiabatic flame temperature. You see if the flame temperature becomes too low, you get very high CO and also unstable flames. And if CO is emission for unstable combustion. And if the flame temperature becomes too high, you get very nice stable flames, but you get very high NOx. So if you really want dry or NOx, where you want to have it for low emissions, you only have a very limited range of operations, and that is really given by the fuel air ratio. In a non-premix combustion, you can operate in a much broader range in this situation. And this is how it can look like for a typical combustor. So I'll try to explain. I think so. What you see here is the air inlet. The air is sucked in. It gets in here. So you see here the IGVs. IGVs is 47 degrees. You see here the compressor, the combustor, and the turbine. There are some fancy things on this situation here. So you also see here the compressor bleed heat, so the compressor recirculation. So you can use this for to get hot air to the inlet of the compressor to decrease load and for stable combustion. So that's actually going on in this situation here. And then if you look, so this is really for the air system here. If you look for the gas system, you see here, here's the gas valve. You have one main control valve that's really to get the right pre-pressure for part load control. And actually what you see here, you have 4 gas control valves. And we come back to that later, but this system has 4 gas injectors. And depending on where you are on a different situation, either on part load or full load, one of these or more of these is an operation. You, for example, see that now 2 of them have closed and 2 are in operation, but really depends on what load conditions you are, depending on the situation. And this is typically situation for a modern gas turbine. They normally have a number 4 or 3 or 4 fuel circuits to really to ensure stable operation at all load conditions. What's the liquid injection? Yeah, this is a system what you hear that can also run on liquid fuels. So that's the question. What's the liquid injection? This system can also run on a lot of liquid fuel, but okay, that's not relevant. But that's they normally have separate injectors for the liquid injection, and probably I don't know, but probably the water here. I should know what I just took it from the internet as a nice picture. But the water is probably used either for NOx reduction or to be used together with the liquid combustion. It can also be like that. Yeah. So this is an example of how it then will look like. So for example, in this situation, this is a DLN1 system from GE, but I think it's typical for a lot of systems. This system has 2 fuel injectors. So there's 1 fuel injector in the center, and then sorry about that. There are 2 circuits of fuel injectors. So there's 1 circuit of fuel injectors here in the center. That's really creating a non-premixed flame. And around that here, you have premixed fuel injectors around here. So what happens here? The flow flows around this liner. So it comes from the compressor, flows around this liner, makes a 180 turn here. Here you have the fuel injectors for premixing. In this chamber, it can be premixed. You see here Venturi. That Venturi is really there to prevent flashback. So in this situation, because there's an acceleration of the flow, so the flow velocity is here than the local flame velocity. And that situation, so the flow is coming out of here, and here you get the flame. Situation. And in the center, you have a non-premixed injector, and that really has the intention to get a pilot flame to stabilize the main flame. So this is a really very standard solution for premixed combustion. So a large, about 80–90% of the flow goes over the premixers, and a small part of the flow goes over the non-premixed pilot flame to stabilize the main premixed flame. Okay. So that's how it looks like. For example, the little more schematic. Flow going around here. So about 81% of the fuel goes to the premix, and 90% goes to this non-premix flame. And there you can guarantee both a low NOx and low CO. But this is the situation at full load. So in combination with inlet bleed heat, you can go to 80% load. The 50% load, you can operate on 50% load. So you can operate the fuel air rate constant here on 50% load. But you see actually on lower load conditions, for example here, it's not able, because you are at a too low fuel air ratio, it's not able to get here a stable premix flame anymore. And in that situation, they create a small number of non-premix flames. Both here, actually, the fuel injectors are used for non-premix flames. And there's also a big non-premix flame here in the center. And if you go to even lower loads, they switch off the main non-premix flame in the center, and you get only those small non-premix flames here at the corner. So if you look to this picture to the right, so how would it look like if you go from full load to part load? Well, you first are in the premix mode, so you are in this mode, what you see here. And then situation, the fuel air ratio is quite more or less stable, so you can have this premix flame. At this situation, your fuel air ratio cannot be stable anymore for a premix flame. So then you switch to this kind of mode. That's in this situation here. And in this situation, the overall fuel air ratio becomes too low. So you wouldn't also not have a good non-premix flame anymore. And actually, then is the local fuel air ratio, you only use these flames here. So you saw the IGV angles. See the IGV angles, they modulate during the premix mode, and they fully closed here. So this is typically, and I think this is a kind of a GE, but I could also have picture from Siemens. They typically have all kind of this situations here for combustion controls. Important to notify here is, for example, if you go from this situation to this one, you should transfer it. So actually you want to get rid of those small non-premix flames here in these corners. So what they do actually is they very shortly put all the gas on the central non-premix nozzle, so they get very big non-premix flame here. So then the flames here extinguished, and then they open these nozzles again, these fuel nozzles again, and because there's a high velocity now here, the flame can't enter anymore into this becomes a premix in this case. Now this situation here, and that's really tricky. These transfers from this situation to that situation, that's really good to have that transfers in combustion. If those are interesting, I can do that at the end. The combustion tuning for dynamics. It's not for the exam, but I have an separate presentation for that. I will ask who's interested can stay at the end to have their second, have a short discussion for that. Come back to that later. So we saved it to the end. For the startup control, so now we have the combustion control, so we have the main control, the combustion control, and then you have the startup control, the sequences you have there. And very important here, well, if you have a startup control, you have the safety checks, you have the start motor, so you have to, very important actually, because a gas turbine can't do anything without an airflow, and to have an airflow, you need a rotational shaft. You need shaft rotation. You need to have the blade should be moving. So you always have a kind of start motor to get the unit in operation. Then you always need a kind of always need purging or venting to remove the flammable gases from the system. Then you can ignite. So you normally do it at a low rotational speed, low speed, and then you can accelerate to full load. If you really look at those situations, the very simple situation here is that the airflow is more or less proportional to the speed. So you can also you can use this. The speed is normally in this situation. So to make a simple controller for the situation, by the speed you can assume what's the fuel air rate, and that way you can more or less control the fuel air rate and control the fuel during that situation here. So what do you normally have? Startup sequence. Well, you get ready to start, then you start a command, then actually the diesel engine starts, so the start motor. The turbine accelerates to purging speed, so cranking speed. Then the purging takes place, so that's really the venting out all of the flammable gases from the situation. When the purge is complete, you go to the firing, then you go to firing speed. So normally the firing speed is below the purging speed, because at purge you want really have a lot of air to have a quick purge to get all the flammable gas out of it. And with ignition, you want to have a low mass flow of air to get a stable flame. Then you get the flame, so then you have the gas flows open, the spark plugs are energized, and in that situation, then you get wait till the flame detected is. If there's no flame within the certain time limit, you get a trip. So trip is stop of the unit. If the flame detected, you go further. Then normally you warm up a little bit, 1 minute or something like that, and then you really increase the fuel flow to accelerate the unit to governing speed, so to reach full speed, to reach the required speed. And then actually, you more or less the startup sequence is finished here. So the standard startup sequence. So if you look like, how should it look in this picture? So I try to show it here. Oh, sorry, about here. So here you have the timing. Here you have the number of parameters. So if you look, for example, here, you get here that the speed, the the speed. So here, for example, is speed. The yellow one is the speed. So you start here. Here you get the boiler purge. So the higher speed, so a higher rotation speed. Then you decrease the speed, and here you get you open the fuel valve. Then you get the ignition. You get the flame. So when the flame is detected, you increase the fuel. You increase the fuel valve to really accelerate the flow. You really see actually normally you have a little bit. You normally add a little bit more fuel than in this situation, really to ensure you get the flame in this situation. And because when you get the flame, you accelerate the unit, so the acceleration speed to full speed and load. In this situation, you also see here the exhaust temperature coming up, just like that. Normally you get a peak, depends a little just before full speed and load, depends on a little bit on that, and drops again. So the full speed and load, you normally have a decrease in fuel temperature anymore because they have maximum airflow also. Then if you're at full speed and load, you get the generator breaker opened. And so you control here. And then actually in this situation, from this situation, can a generator open, you also see loading of the gas turbine, and then you make power. So these are typically duration of a typical gas turbine. Well, actually, this purging is really short, and normally it will be something like 10 minutes. But without purging, but with purging, you can really get the gas turbine from no speed to full speed about 50 minutes, and then you can really increase the load depending on your design of your gas turbine. So this is typically your gas turbine loading. There's a question. Should it not be breaker closed? I have to check the breaker open, or breaker closed. Yeah, it should be checked. It should be breaker closed. It should be breaker closed. I fully agree with you. Yeah, there is breaker closed. This the here you synchronize to the grid. So here you breaker closed. That's true. Yeah. Yeah. Well, the same picture, but a little bit different situation here. You get actually the same situation here. Then you get here the acceleration of the speed. You get normally this bump in exhaust temperature at full speed no load. So your synchronization, you get the minimum, and then it goes up again depending on the power. And here you see the exhaust flow. So you really see here the increase the exhaust flow. Does the mass flow because you suck in more air because your rotating speed, you get more faster here, get constant here, and here you open the ITVs and you have full load. So you also hear the full load situation here. And this situation, well, it is 50 minutes to full load. Well, these are typical numbers for gas turbine. Depends a little bit on what gas turbine you have here. Well, actually, with air or engines control, well, first of all, at startup is maximum power. Actually, there they really work on the outlet temperature control to have that maximum power. And at cruise, they have maximum efficiency. So you really want to have a high pressure ratio and one as high as possible. And they control it, of course, with a combination of the fuel flow and the inlet guide vanes. So for example, if you see like here, but take off, for example, if you have the, I see it here, take off. So this is the cruise speed, average rate for some numbers. You, for example, see that the temperature at takeoff at the stator outlet is about 1783 Kelvin, and you see during cruise it's a much lower, and you see the rotational speed is also as high as possible to get the high pressure ratio here. Number of situation. So what's the summary? So the startup sequence is really where you have the bleed valves and ITV we just discussed to prevent surge and stall. That's normally forward control. That's really depending on the speed. They normally go open and close. So for the normal control, you have the PID control with the ITVs and the fuel control as the control actuators, as controllers. Then you have the material limits, the turbine inlet temperature. So that's controlled by both ITV and the fuel using that exhaust temperature control. And for combustion, you have scheduling of the burners depending on fuel air ratio. And that's more or less equal to the turbine inlet temperature. So this is about, I want to discuss for the exam and really the class about controls. Are there some questions? And if some people are interested, can have a short introduction on combustion dynamics and controls. But are there still questions on this class on the controls? I don't see any remark here. So then I stop this situation on the combustion, on the controls, and then we'll have a short introduction about combustion dynamics. So if interested, I can give that. It's a little bit different. I will open all our presentation. If you have some more minutes, I can open it. So I have to share screen. Yep. Okay, wait a minute. Yeah, this is this is a study I performed when I worked at Electrabel, the previous name from Engie in 2005, 2006. And together with a colleague of mine, Klaas Boonstra, we did a lot of issues with dynamics, and we did some study on that and some improvement on that. So that's really about combustion acoustics in gas turbines, and really how can you control it. An example, this from GE gas turbine, but Siemens and all the manufacturers do similar things. Mitsubishi do similar things. So that's not part of the exam, but it's for interested people. Let's start. And actually, this is the reason why you don't want to have combustion dynamics or humming, what you look like here. So you will see actually two situations here. On the right side, you see a line that is damaged. And really what happens is combustion and dynamics are, it's acoustic vibration in the system. And the amplitudes can be that high that also the materials start to vibrate. And if the material starts to vibrate, you can have a high cycle fatigue in material. So you can see it like here. And if you have high cycle and fatigue, you get cracks. And if you get cracks where you get things like that, you don't want. This is situation actually the same. This is a burner nozzle. So you see actually the 5 fuel injectors from a 9FA gas turbine. And actually what happens here, there were very severe combustion dynamics in the system. And because of this high combustion dynamics, the premixing tube got loose in this situation. And by the premixing tube getting loose, well, actually that came into the flame, that's melted, and then the flame flashed back. So you get all kind of this, the whole the burner system is completed. To be honest, GE now solved the problem. So there was a temporary issue at that period from GE, but now it's really solved. So there's no issue anymore. But that moment with this DLM 2.0 combustion system, they had the issue with combustion dynamics. And it's what you want to prevent. It costs a lot of money and it costs a lot of outage time. And actually the impact is also larger because if you get those loose parts from the combustion chamber, they also travel downstream into the turbine and you can have damages like this to the turbine. So that's even more expensive. So this is the 9FA. So this is the 9FA from the at the Eems power plant in the Netherlands. So it's the north of the Netherlands. There's 90 technologies, and actually in 2010 they switched from DLM 2.0 to DLM 2.6. So, but the presentation I will give is about DLM 2.0, so the previous combustion system. And here you see those are typically, well, it's a 9FA, how big it is, one of the biggest gas turbine that's in the world, comparable to the current Mitsubishi, Siemens, and all those gas turbine. So you get here the air inlet, compressor, combustor, and the turbine, and this goes into the boiler. So this is the cross section of the combustion chamber. Actually, you see the same here. So actually, the air flows comes from the compressor. So it's lifted here by the compressor, flows around the combustor. I really have to show you, flows between this and this flow sheave, flows here, turns 190 degrees and enters in the 5 pre-mixing tubes you get here. You have a number of injectors. So you first have the injectors here, even upstream of the burner. So these are called the solidized quaternary gas injectors. And then you have quaternary, so the 4th type of gas injectors. You have the primary one gas injectors, they are here. And they are the central ones, they are the non-premix flames. And they have the tertiary and the secondary ones. We come back to that later. So you have 4 fuel circuits in this one. So you get here the fuel injectors, you get here, when it's all, everything is white, you get here the premix flame. And then the flame goes and the hot gas go into the turbine with the transition piece. So this is how it looks like. So you have the 5 fuel injectors. So if you start on full load, from those 5 fuel injectors, 4 of them are connected together. They are called PM4, and that's called the secondary one. This is a secondary injector, and PM1 is the tertiary one. And actually, this important one, the most important tuning is the fuel split between PM4 and PM1. So by using this fuel split between PM4 and PM1, you make flames unequal. And by making flames unequal, you can prevent combustion damage. We'll come back to that later. So this is really the premix mode. If you start from ignition, you start from diffusion mode. So then you only run on the primary nozzle. And then you have 4 primary nozzles. So you get 4 4 non-premix flame. Then from about 81% speed to 40% load, you have those 4 non-premix flame and 1 big premix flame from the tertiary nozzle. Then you have a transfer mode, piloted premixed, and then you go to fully premixed. So this, you have those 5, so if you look like here, you have those 5 segments here, the 5 injectors, those 5 injectors, and how do they look like? So you have here the inlet, you have here the swirl flame with the fuel injectors, you have the premix tube, and then you get the exit. And this is the diffuse tube, so the primary fuel goes to this one, and the secondary or tertiary fuel mixture goes to this one. So the primary fuel you only use during startup. So this is also how it looks like, more or less. You have here the air coming here, in the premix fuel of air, and then it goes like here, this for the non-premix flame. This is how it looks in reality. So you here get the 5 premixes connected together, where 4 of them are connected together, and there's 1 separate. And I think that's very smart. By using from GE, by using 4 plus 1, you create an asymmetry. So that's really important to create an asymmetry for combustion dynamics. And this is typically, if you look like combustion dynamics, and if you look like humming, or what you call like it, you get a kind of spectrum like this. So you see here frequencies, and you have a number of peak in that frequency. So you have the dynamic pressures, you have number of peak, and each combustion chamber has its own peaks. That really actually the combustion chamber is just an organ pipe with its own acoustic eigenfrequency, and that really determines these frequencies. And so these are normally low frequencies, medium frequencies, and high frequencies with all different situations. Where you can have all those different frequencies. We did some number of acoustic studies for that, how the motors look like. So you have the 56 Hertz tone. You have the cold tones, they are called. You have the 150 Hertz tone. So if you look like this one, they all here, the 56, the 120, the 150 Hertz. These are the all imported calls. And actually, this is very important to see how does such a situation look like. Important actually, if you look like a situation for the combustion dynamics, is that the flame amplifies the acoustic vibrations in the combustor. So in the combustor, you have acoustic fluctuation. Acoustic fluctuations are nothing more or less than pressure fluctuations. And that pressure fluctuations can trigger fuel flow or airflow fluctuations. So if you have here pressure fluctuations in the combustion chamber, that trigger those airflow fluctuations. That airflow fluctuations trigger equivalent ratio fluctuations. And by those equivalence ratio fluctuations, you get different flame speed. There you get flame fluctuations. And if you have the fluctuating flame, that generates sounds again. And that sound generated by the fluctuating flame, if it couples with acoustic eigenfrequency, then you get the pressure fluctuation, the mass flow fluctuation, the flame fluctuation, and you get a circuit loop. And if it's all tuned very nice together, you get amplification of the acoustics by the flame. And actually, that's exactly the same if you have an amplifier and a microphone. So if you put the loudspeaker too close, if you put the microphone too close to the loudspeaker, you get that woo effect. And actually, that's exactly the same here, where the flame is the amplifier. And the flame is the amplifier that amplifies the sound always present in the combustor, because you have always some rumble, some turbulence, some turbulent noise. And if it's amplified by the flame, you get the instabilities and combustion noise. Now, one of the tricks you can do, for example, is playing with the quaternary gas. So one of the tricks, for example, this situation do, if you look here, you can, in this situation back here, you can inject gas upstream of the normal burners. And by adding some extra gas injection situation, you prevent that, for example, equivalent ratio fluctuation occurs. And this situation, what happens here, if you get here the acoustic fluctuation here in the combustor, that triggers the airflow fluctuation, airflow to the burner. By fluctuating airflow to the burner, you get a fluctuating airflow at the fuel injection location. So if you have a constant fuel injection and a fluctuating airflow here, that means that you get also fluctuating fuel air ratio locally. Well, that fuel air ratio locally is transported, with a local velocity to the flame, and that creates then flame fluctuation. If you have temporary a local low fuel air rate, you get a lower flame velocity, so you get a smaller flame. And if you have a high fuel air rate, you get a higher flame. So in this situation, by this triggering of this fuel air ratio fluctuation by the airflow fluctuation, you can really have that amplifying effect we just discussed. And the trick now is, if you add some fuel upstream, then you get you don't have the fuel airflow fluctuations anymore here, and that really dampens the effect. The other trick that is done by GE is, because they have 4 burners connected and 1 burner separately, by giving them other settings, so other basic fuel air ratio, we have different flames. So that means that these flames will react differently to the acoustic fluctuations in the combustion chamber. And by changing this split, so the different basic fuel air ratio for this one flame and this 4 flames, you can also get, they don't all react the same, and therefore you can also detune the system. So that are some tricks you can do with combustion air ratio and things like that. Yeah, so this is one of the things, and this really one of the things. The 150 Hertz spike also coincides with the material eigenfrequency of the liner. So that if you get a high fluctuation in the liner, also the metal of the liner can fluctuate, and it can lead to this kind of fatigue cracks. So you see here the eigenfrequency of the liner just coincides with that. Then you have this one, this other eigenfrequency, not that interesting. This is an important one. It's called screech. So this is one of the most tricky ones. So then you have a kind of radial acoustic eigenfrequency. So it's not a longitudinal, but a radial acoustic eigenfrequency. And that couples very nice with the situation here. And then you are really kind of vortex setting. So we did the kind of studies there. And for example, you see, for example, here a flame that's also modulated. And it appears from our study, and I'm not going to detail a little bit here, but this Struwel, so this really eigenfrequency coincides with the Struwel eigenfrequency of the premixer. So in this case, if you have a fluctuation at these 2300 Hertz, you get a vortex setting from the premixer, and then you get a flame that reacts very strongly to this, and therefore you get a very strong interaction between the flame and the acoustic, and therefore very strong coupling. You can prevent this if the four flames act different than the single flame. So there are some tricks to really prevent this kind of interaction. So really the equal split, you really should prevent for combustion dynamics, you should be equal split, you should be have conformity of flames. And I think, well, that's one of the challenges also with Siemens gas turbines. Siemens gas turbines normally wants to have it as equal possible, but actually for combustion dynamics, you should have it unequal as possible. So that's really important. If you really want to get rid of combustion dynamics, make it as unequal as possible. I think that's one of the tricks you can do there. Yeah, so this is one of the screeds. So what happened is what I said actually is if you had that high 2300 hertz, you get actually liberation of these premix tubes because the crack weld was not good. Kind of bad things like that. And actually it's on down. And actually, so this is the solution prevented by GE as a cap resonator. So actually they damp now the acoustics in the system by adding a resonator, by absorbing the acoustic energy. In this case, the amplification by the flame is smaller than the damping by the flame from this resonator. So these are a lot of those manufacturers use kind of these resonators to get acoustic energy out of the system, to damp the acoustic energy around these typically dangerous frequencies. So this is really how something like tuning looks like. So that's normally when you do tuning, actually, what you do is normally you vary the split. In this situation, it's the split between, like I said, the PM4 and the PM1. So the 4 connected burners and the 1 connected burners. So an 80% split, you have equal split. So then 80% of the fuel goes to PM4. So 20% to fuel and 20% goes to the PM1. So in this situation, these are the number of situations we tuned here. And actually you see two things popping up. So if you get too close to even split, so too close to 80%, you see that the screech amplitude comes up. So here the tuning parameter is the turbine inlet temperature. You see the screech coming up. If you have too far away from even split, so you have much more fuel to the PM4, you see another comes then in this situation 150 hertz comes up. So really you want now a tuning schedule just in between those two islands. And this really the Fingerspitzengefühl are really, how do you really tune this wise between those two areas? So you should really be aware what combustion dynamics incident can take place at that situation. And they shift a little bit with frequencies. Modified gas index has important. That has because what's the impact of the modified gas index? It has both impact on the pressure drop because the gas fuel injectors, like I said, the coupling can be directly either via the airflow or via the gas flow. But the Wobbe index also has impact on the fuel air mixture because that's impact on the impulse of the air injection into the fuel injection into the air. So I think the Wobbe index is really normally very important parameter to control combustion dynamics. So this is the short presentation I'd like to hold about combustion dynamics. I don't know if there are questions about it and tuning of combustion dynamics. No, I cannot share this presentation because it's for my Electrobel employer, so I cannot share it unfortunately. I can maybe, no, I cannot share it. No. More questions? No more questions. Then I really want to stop the class for now. I think we're finished. Thank you for your attention. So coming Friday, I see one question coming up. Coming Friday, we will discuss the classes. Would you use another thickness of the housing in order to change the eigenfrequency? Yeah, okay. You should be aware that the question, would you use another thickness of the housing in order to change the eigenfrequency? There are two eigenfrequencies. So the real issue with combustion dynamics is really the acoustic eigenfrequency. So of the acoustic system of the air system, the combustion system. So then it's not the thickness of the housing does not change the eigenfrequency of the acoustic system. It can change the eigenfrequency of the hardware, but I think you should first prevent the acoustic dynamics, and then you can maybe change. You can change the eigenfrequency, but normally then it also pops up an other eigenfrequency. So it's an inherent of the system depending on the eigenfrequency. You can detune, of course, the acoustic eigenfrequency from the hardware eigenfrequency to prevent damage. There you can maybe do something with the design, but I think that's a secondary measure. I think the first measure should really be to reduce the acoustic coupling system. Okay, I think that was all for the combustion dynamics. So next Friday we will have a class on where we discuss the exam. I wish you a good, nice evening, and good luck, everybody. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Okay, thank you.
Thank
Bye.
you. Bye-bye.